All right. So now we've already found our slant asymptote, um, and I just wanted to do that first for everyone that needs to leave. But now I'm going to finish the rest of this problem. Now, if this was a normal problem and I was doing this normally, my first step would be factor everything. So that's what I'm doing now. I'm going to take both my numerator and denominator, and I'm going to. Now, lucky enough for us, they already factored out a GCF in the numerator of x. So now all I have to do is factor that. Why won't it zoom in? I have to factor that quadratic. So I'm going to create my little x. A times c is -3, b is 2. What multiplies to -3 but adds to 2? 3 and -1. And I don't have an a, so those are my true factors. So this is x times 3, x minus. And then in the denominator, guess what? That's the difference of squares. It pops its head again. This splits into x 3, x minus. Now we should immediately notice here that we have a whole created by this x plus 3 over x plus 3. So the x plus 3's will cancel, creating a whole. I'll go ahead and write it down at the x value of -3. And I know that I'm going to have to find that y value eventually. I'm not going to do it with this yet. So here in factor form, this is x times x minus 1 over x minus 3. And we remember that, oops, okay. We remember that the 0 remaining in the denominator creates the vertical asymptote. So here, the factor of x minus 3 gives us a 0 at x equals 3. So my vertical asymptote is at x equals 3. So now is as good a time as any to finish finding the whole. All I have to do is take that -3 and plug it into the factored version of our problem. So we have a -3 times -3 minus 1 over -3 minus 3. So -3 minus 1, that is a -4 times a -3, that's a 12 over -3 minus 3, that's a -6. 12 divided by -6 is a -2. So my whole is at -3, -2, -3, 1, 2, 3, -2. Okay. And then I am going to find my x-intercept and y-intercept. We find our x-intercept by the zeros in the numerator. So our zeros in the numerator are x equals 0 and x equals 1. So my x-intercepts are actually 0, 0 and 1, 0. So we have 0, 0, and I should do a different color other than purple, huh? Okay, 0, 0 and 1, 0. Our y-intercepts are found by substituting 0 in for x in the factored form. So I have a 0 times 0 minus 1 over 0 minus 3. So anything times 0 is 0. Anything that has a 0 in the numerator is just 0. So our y-intercept is also 0, 0. Which makes sense because it was an x-intercept as well. All right. So now for the rest of this problem. Obviously, this graph is not continuous. I do have a vertical asymptote, which I haven't drawn yet. I should go ahead and draw that at 3. This is x equals 3. And I also have those symmetrical points. So if this is our center, so we can go over to up 5, but I almost think in this case, instead of thinking of this as symmetrical, I'm going to show you how you would do this on a calculator. So can I move this? All right. So here I'm going to plug this entire thing into my calculator and making sure my numerator is in parentheses and my denominator is in parentheses. So I have x cubed. Now in this case, because you're just distributing the x in, you can either write it as the original, or you can distribute the x in and type that polynomial in. In this case, I am distributing and then typing because it's less work. Just a little tiny bit. Not really, actually, now that I think about it. And then divided by x squared minus 9. And we're going to take a look at the graph. Now I already changed my window so that I could see this top curve more easily. I just made the y max a 20 because before I could only see like a little tiny portion of it, and I wanted to see a little more. And to help you graph this, yeah, it's useful to see the graph, but more useful is your table. So here we have 0, 0. I already have that graphed. We have 1, 0. Already have it graphed. We have 2, negative 2. Did I graph that one yet? Nope. So 2, negative 2 I can put on my graph. Oh, let's do red. I can also put 4, 12. Well, that's off my graph. I won't put it, but we have 5, 10. 1, 2, 3, 4, 5. All the way up here at 10. We also have 6, 10, which are those two symmetrical points I was talking about. And that's off the graph. So I guess that's it. That's all we'll put. And then I just draw my curves. Again, I'm just kind of drawing them approaching my asymptotes. Now the reason why this one is tricky is because between these two symmetrical points here, our graph actually goes a little bit higher, and it's not a perfect point. Meaning, if I'm talking about my range, I start at negative infinity and I go to this max, this local max point here that isn't a perfect point, and I don't know where it is yet. So what you have to do is you have to find it. All right. So first what I'm going to do is I'm going to find both my local max and my local min. Starting with my local max. You go second trace, maximum, left bound, get to the left of your point, right bound, get to the right, guess, get about on it, which I know it's between 0 and 1. So this is my maximum point, local max, sorry, 0.55, comma, 0.10. My local min, I find the same way, but second trace minimum instead. And I have to scroll all the way over to get to the top curve there. Left bound, and then, whoops. And then right bound, get to the right of it, guess, get about on it. And we have 5.32, comma, 9.91. So now we can answer the question of where are we increasing, where are we decreasing. We can also answer the range and domain. So why don't we go ahead and find the domain first. Now, here, my lowest x value is negative infinity. And I stop at my hole, which has an x value of negative 3. I start back up again on the other side of the hole at negative 3, and I go to my asymptote, which is at my vertical asymptote, which is at 3. And then I start back up again at 3. This is interval notation. My range goes from negative infinity to the y value of the whole, which is -2. Then we stop at our local max's y value, which is 0.10. And then I start back up again at that y value to infinity. So then I need to go ahead and find the decreasing. So I'm decreasing when I'm, remember, increasing, decreasing, you're reading left to right and you're asking yourself, where are you going down? So you start going down at that local max's, now increasing, decreasing is always the x value. So you start decreasing at the x value of 0.55 and you stop at the vertical asymptote of 3. And then you start decreasing again on the other side of 3 back at the top here. And then you stop decreasing at the local min, which is 5.32. And now you're increasing. So that was decreasing, and now the increasing is going from negative infinity x value to that local max 0.55. And you start decreasing again, or I'm sorry, increasing again at the local min, which the x value of the local min is 5.32, and you stop increasing at infinity. Whew. And then quickly, continuity. This graph is not continuous. You can't, well, not non, it's not continuous. You can't run your pencil over it and not pick it up, so you would say not continuous. And even though I say that it's symmetric with respect to the center of the asymptotes, this is not what this symmetry is asking. This symmetry is asking, is it symmetric with respect to the y-axis or the origin? If your answer is no to both of those, you would say it has no symmetry. We mainly want to know symmetry because of even or odd functions. Now, boundedness here, that's just asking, is this graph bound by any points? Well, yes, it is bounded above at that local max. And whenever you're asking about boundedness, it's actually asking about the y values. So you're bound at the y value of 0.10, and you're bounded below, can't go any lower than that local min at y equals 9.91. Okay, and that's it for that problem.